Well, hello and welcome YouTube. Brandon Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day in my virtual classroom. I'm actually doing this live with my class in session right now. They can't talk to me. I just took my headphones off. They have no idea. I have no idea what they are saying. I'm going to do a solution guide video for them though, working with perpendicular lines and everything regarding angles and perpendicular bisectors. We had a problem set of 12 problems long, I do believe. I'm going to go over those right now, and once this gets uploaded, there will be a timestamp for every problem in the description section down below. But these should go relatively fast here. I have less than a half hour to do this. Let's get cracking. Now, something's already pre-done and color-coded right here. Let me get rid of those, and I'll redraw them again if need be. So sorry, there is a student that's saying that I'm not recording. I am recording personally on my computer. This is not going to be a Zoom lecture. This will be a YouTube upload. I do want to make sure that I respond to that. So this actually is not going through my Zoom. All right, so the first problem actually starts with number 5, and with this diagram, numbers 5 and 6, use the diagram to find the lengths. BP is the perpendicular bisector of segment AC. CQ is the perpendicular bisector of segment BD. AB is equal to BC is equal to CD. These are lengths. The length of AB is equal to the length of BC equal to the length of CD. They mark those there. Now, some other things I want to do here. I did just make the drawings a second ago, and I'll do it one more time. If you can kind of just differentiate here, consider this to be not really a triangle, but really just look within this area right here for a moment and ignore all the rest if you can. Right here it says segment BP is the perpendicular bisector of segment AC, which means it intersects with it at a right angle right here, and it does cut this segment in half to 2 equal lengths. You do already know that the lengths are equal, but when they call the perpendicular bisector, we can see even more certainly the perpendicular bisector theorem states that if there is a point that exists on your perpendicular bisector, it is equidistant from the endpoints of the segment that is being perpendicularly bisected. That means that segment AP is congruent to segment PC, or the length of AP is equal to the length of segment PC. Another statement that we can use for number 5. Suppose AP equals 5 centimeters. What is the length of segment PC? Because these two are equal in length, and because AP is length 5, PC is also 5. PC is 5 centimeters. Now, one thing I want to mention here, this is something I didn't get to talk to with my class a bunch, specifically with segments here. And I do answer this. If you guys check my Q&A Power Hour video, I think I mentioned it in one of them where someone asks, why do we sometimes have an M in front of angles, and then sometimes we don't at all? So if I say M in front of angles, and sometimes we don't have some at all, that's because this talks about the measure of an angle, and this talks about the angle itself, physically, looking at the angle versus what the number is for the angle. Same thing for segments. If I'm talking about a segment right here, like segment PC, I'm saying look at this segment right here. You see PC? PC's right there. But if I say length of PC, another way of writing that is just writing PC without a bar above it. So if you see something that says PC right here without a bar, that means length of PC. Just like these, length of AB equals length of BC equals length of CD. So segments are congruent right here, and then their lengths, their measures are equal. Their lengths are equal. Segments congruent, measures equal. PC is 5 centimeters. Moving on. So you can either write length of PC is 5 centimeters or PC is 5 centimeters, as long as it either has the bar here or doesn't have the bar there. Anyway, moving on. Number 6, suppose AP is 5 centimeters like last time, and BQ is 8 centimeters. What is the length of QD? Well, let's let's look at this other triangle here, because once again we have another perpendicular bisector as mentioned. QC, this segment, intersects perpendicularly with BD, and it is the bisector of it, which means these parts are congruent. They already stated all three of these are equal here, but of course, as a perpendicular bisector, if Q is on it, that means this point is equidistant from the endpoints of the segments B and D, so these two parts are congruent to these two parts. Now, does 5 have anything to do with what I need to find with the length of QD? I don't think so. BQ is 8 centimeters. I think this is enough information to say if this is 8, then this is also 8, because the length of BQ equals the length of QD. Therefore, the length of QD is 8 centimeters, because the length of BQ is 8 centimeters. I'm gonna quickly check my Zoom chat because I went away, so I'm checking. Okay, no one put anything. Okay, those are numbers 5 and 6. Number 7. Ooh, part of the same visual. Let me go back and copy and paste it over. So number 7 and 8 continue on with this diagram. This information, really. So let me take all of that. Give me one moment and put it right there. Perfect. But not perfect. Let's put it on top, shall we? Oh no. There. Right here. Okay. Thank you. Suppose AC is 12 centimeters and QD is 10 centimeters. What is the length of QC? AC is 12 centimeters right here. Automatically, and I can't guarantee this is something that we need yet, but automatically, this tells us, if these two parts are congruent, that this can be divided into 2 equal parts, 6 each. Just know they're 6 centimeters each. 6 each here. That's good information. I don't know if it's useful yet, but it's good. QD is 10 centimeters. So we got 10 centimeters right here. Now remember, if these two are 6, the devil has surged. This one's also got to be 6, right? 6. Oh my gosh. All right, so this is also 6 centimeters. Now, why is this useful for trying to find the length of QC right here? Well, QC is the perpendicular bisector of BD, which not only means it divided this into 2 congruent parts, which we're already aware of, but it also means it intersects perpendicularly. And what that means is, guys, we're looking at a right triangle right here, a right triangle. Now, one other thing that we're talking about here in this section is the Pythagorean Theorem, that the sum of the squares of your 2 legs equals the square of your hypotenuse in any right triangle. Let's say I assign this some unknown x value right here, because I don't want to call it QC over and over. So this x right here, if I square it, and if I add it with 6 squared meaning the other leg, x squared plus 6 squared equals 10 squared. This is the Pythagorean Theorem. This is a squared plus b squared equals c squared. Let me write that thing out in case it shows up again. The Pythagorean Theorem says if a and b are the legs of your triangle, right triangle, and c is your hypotenuse, then the relationship is always as such: a squared plus b squared equals c squared, which can be proved, by the way. A, B, C. Doesn't matter which one is specifically A or B, as long as they are the short sides, the legs that make the right angle. All right, 6 squared is 36. 10 squared is 100. Subtract 36 from both sides, x squared equals 64. Take the square root of both sides, you'll get x equals plus or minus 8. Now, we can't have negative length. We can't have negative length, so we're going to consider its absolute value and only refer to 8. So the length of QC is x, so I'll just call this QC now. QC is 8, and this is centimeters there. So again, using Pythagorean Theorem and the perpendicular bisector theorem to understand that we have that right triangle to find the length is what we needed. Number 8, suppose the length of PB is 3 centimeters. Okay, I'll suppose it. Suppose it's 3 centimeters here. And AD is 12 centimeters. So this whole thing is 12. And if you just saw last time when I divided it by 2, because there were 2 congruent parts, now there are 3 congruent parts. It is trisected, if you will. That means this is 4 centimeters, 4 centimeters, and 4 centimeters, dividing 12 by 3. What is the length of PC? Well, just like last time, guys, looks like we're looking at another right triangle right here, as it was a perpendicular bisector. That's a right angle. And we have the leg lengths 3 and 4. This becomes 3 squared, well, let's see, call this x again, 3 squared plus 4 squared equals x squared. You might learn some things soon called Pythagorean Triples, in which case you would have known this was 8 off the bat if you know anything about it. I actually know this answer is 5 without doing anything with it. This is called a 3, 4, 5 special right triangle. 9 plus 16 equals x squared. X squared is 25. Take the square root of both sides, x equals plus or minus 5. We know that part. However, only positive units, and let's have a unit of measure and call it PC. So the length of PC will be 5 centimeters. All right, Pythagorean Theorem at play. I kind of hope, I'm not certain right now, but I kind of hope we get one in Pythagorean Theorem where we find the length. Oh, no, we just did that right here. Find the length of a missing side. So notice why I used 3 and 4 on this side here, because they were the legs of the right triangle. Whereas last time we were trying to find a leg when we knew these two parts right here. Okay. Numbers 9, 10, and 11 are based on this diagram. These diagrams can end up getting a little more confusing over time, and I'm certain that we're going to be able to look at some more confusing diagrams and differentiate parts. Just make sure you know your angle relationships at play and what things we have. Obviously talking about a lot of perpendicular bisectors here and there. All right, given that PA equals PC, those are lengths. The length of PA is equal to length of PC. That means these segments are congruent. So if I put little tick marks here, guys, what we learned was also the converse of the perpendicular bisector theorem. The perpendicular bisector theorem states that if you have a perpendicular bisector, such as this perpendicular bisecting that, then it makes these two parts equidistant. The converse also holds up, and the converse states if you have a point that's equidistant to endpoints of a segment, then it is on the perpendicular bisector of that segment. So P is equidistant to A and C. Therefore, it exists on the perpendicular bisector of AC. So this line that's going down right here, if it's going through that midpoint, they say BA is equal to BC. That means it's going through the midpoint. Then it is perpendicularly bisecting it. Okay? We know that's going to be a right angle as a result of the knowledge that these were equidistant and these, in effect, were equidistant, that's perpendicular. All right, suppose the measure of angle 2 is 38 degrees, find the measure of angle 1. So that knowledge that it becomes the perpendicular bisector means we know with this right angle here that angles 1 and 2, which are adjacent and make a right angle, are complementary. Measure of angle 2 and measure of angle 1 add to 90 degrees because they are complementary angles. They form to make that right angle. That's through the knowledge of the converse there. Measure of angle 2 is 38 degrees, so the measure of angle 1. And here's an example of showing work, kind of getting in that instance. Now that I subtract 38 from both sides, you don't have to write minus 38. This is straight up algebra, and that equals 52 degrees by nature of being complementary. Number 10, suppose that PA is 10 centimeters, the length of PA, and the length of PB is 6 centimeters. What is the length of AC? Now, AC is the entire thing right here. Use a different color. AC is the entire thing right here. What we are aware of is we do have a right triangle that exists right here. Right here. A right triangle that exists. Listen, as far as work goes, I'm going to save some time myself. We already did a right triangle that had 10 and 6. 10 is the hypotenuse, 6 is a leg. So I already know my other missing leg is going to be 8. I know my missing leg is going to be 8. I'm going to save myself some time. I'm going to save myself some time and say the work is shown here with the same kind of thing and say, if that's the case, if this is 6 and this is 10 in the right triangle, AB is going to be 8. I know that the length of AB is 8 centimeters because I already did Pythagorean Theorem on that. But knowledge that this is a right triangle had to take form. Now I need to find the length of AC. AC is the length of AB plus the length of BC. AC is the length of AB plus BC because they are collinear segments. Whoops. They're collinear segments here. Now, AB is equal to BC. We already know that. And BC, therefore, is 8 centimeters. So we know that we have 8 and 8 added up here. AC is 8 plus 8 is 16 centimeters. Because they are both the same length, I just kind of add them up or double them up, and then I'm good to go. 8, 8, 16. That's the whole length. Okay, find measure of angle 3 plus measure of angle 4. There are a lot of ways to do this one here. They are asking for the measures of both of them together. I mean, a lot of different ways to talk about this. For one, let me kind of erase everything here except for the right angle. For one, we knew this was a right angle here because of the perpendicular bisector nature, the converse perpendicular bisector theorem, all that stuff. We know that that's the case. If that's the case, we have vertical angles right here. This is congruent to this. Vertical angles are congruent, so if one is 90, the other's 90. That means the measure of angle 3 plus measure of angle 4 is 90 degrees because vertical angles. So that's one way we could do that. Just straight up vertical angles. If two lines intersect, once one of them is 90, all four of these are 90, guys. One's 90, the other's 90, the other's 90. And that's probably a concept they wanted to throw in because I know they have a theorem or something on that says that a straight angle that has two adjacent angles that are a linear pair that are equal to each other means both of them will be 90 degrees. So if one's 90, the other's 90. If one's 90, the other's 90, like that. And it just keeps going. Another way with vertical angles, guys, is just, and here's the thing. Notice how they say suppose here. I think that's hypothetically just for this problem. Measure of angle 2 is 38 degrees. I don't think we can assume that's going to be 38 degrees for the rest of the problems. But if we could, and this was 38 and this was 52, well, 1 and 4 are vertical angles with each other, so that's 52. And 2 and 3 are vertical angles with each other, and that's 38. So if we add those two up, we still get 90. Now, again, I don't know if we're supposed to be doing that. I think once the number changes from 9 to 10 and such, we're changing the nature of the problem. So I think just talking about the vertical angle thing is good in and of itself. We don't need the individuals anyway. We just need to know what they add up to. And I think that's part of the point. So I'll leave it at that, 90 degrees. All right, moving on forward here. Confusing drawing, a lot of stuff here. Given M is parallel to N, so these two lines right here are parallel. X is parallel to Y. Hopefully you know what these arrows kind of mean. It's parallel. And Y is perpendicular to M. So Y is perpendicular to M. We're looking at that right there. Use the diagram to find the angle measures. Before I do anything with numbers 12 and 13, what's some other information we can find out here? Excuse me. I have, and I hope you can recognize this here. This goes back a section or two. I have two parallel lines here cut by a transversal right there. I know that this is 90 degrees. That makes this 90 degrees because they are corresponding angles. Boom, got right angles right there. Likewise, I have two parallel lines. Two parallel lines here cut by a transversal here. Once again, corresponding angles. If this is 90 degrees, then this is 90 degrees right there. And all of these things, guys, if you do the two parallel lines cut by transversal bits, you can make corresponding angles, make all these things. Everything here is a right angle. You can make all these things 90 degrees as needed. So I'm going to draw all the right angle symbols in case that's useful for the information that we need, such as there are sets of complementary angles here and there, which I'm playing with. So all those right angle symbols, guys, may be relevant to what we're doing. I haven't seen the problem, so I couldn't tell you one way or the other. But when they give that information and they say one's perpendicular, kind of makes the other perpendicular once all these lines are parallel, which is nice to talk about. And you all already know that's a right angle, things like that. All right, suppose measure of angle 7 is 30. Find the measure of angle 3. Okay. Ooh, interesting. So 30 degrees on the measure of angle 7. It's way the heck up here. And they say find the measure of angle 3. I want to make sure I don't give you any indicators of stuff that we haven't seen before, so I got to be careful with the way that I say this. But because this is a single... Oh, okay, so here's what I'm going to do. Because this is a single line... Here's another one, guys. I got two parallel... Let's see which lines I want. I got two... Ooh, this is going to be hard for you guys to decipher, so do the best you can when you look at this. Two parallel lines right here. New transversal. Line A. Line A is my new transversal. I hope you can ignore the X and Y, all those lines here. Look at the blue lines. Two parallel lines cut by a transversal. Here's angle 7. I'm not going to look at angle 3 yet. I don't have a relationship with 3 because 3 is formed using line X and line A. But angle 2 right here, if you can see that, kind of tilt your head to the side. If you can see that, guys, we are looking at corresponding angles right there. If 7 is 30, then 2 is 30. Measure of angle 7 equals measure of angle 2 because those are corresponding angles. I don't know if this is the only way. This isn't the only way to do it. There are other ways using... There's actually a second way I'm looking at right now. Actually, it doesn't get me any closer to it or any faster to it. But because those are corresponding angles, those measures will be equal. So this is also 30 degrees. So hopefully you can kind of decipher that bit. It's a little harder without being able to draw the blue thick lines like I can. But hopefully that kind of helped. I got to make speed a little bit here. So measure of angle 2 is also 30 degrees, as 7 was. Now, 2 and 3 are complementary. 2 and 3 are complementary. They add to 90 degrees. There's the right angle. Measure of angle 2 plus measure of angle 3 equals 90 degrees. So measure of angle 2 is 30. 30 plus measure of angle 3 is 90 degrees. Therefore, measure of angle 3 is 60 degrees. Subtract 30 from both sides, and we get 60. Again, there are other ways to do it, some of them involving what's called the triangle angle sum theorem or something. I forget what it's called. Interior angle sum theorem. But we haven't used that. So I'm going to go based on the parallel lines bits. And that other line was kind of useful to make that happen, because the two parallel lines there. All right, suppose measure of angle 1 is 90 degrees. So once again, just as far as talk goes, I'm going to erase anything that was irrelevant. Oh, I erased everything. I don't want to erase everything. Let's erase things that were only relevant to that last problem. Suppose measure of angle 1 is 90 degrees. Okay, at least that follows suit with what I drew before. If this is 90, that's 90. What is measure of angle 2 plus measure of angle 3 plus measure of angle 5 plus measure of angle 6? Well, 1 is 90, and 1 makes a linear pair with the 2 and 3 conjoined. So 2 and 3 are, you already know they're 90, but like if you didn't know that information, we can use that now to say that they're 90. Because 90 plus 90 equals 180. This is a linear pair. So measure of angle 2 plus measure of angle 3 is 90 degrees. 5 and 6 are in the same boat here, because they're vertical angles with 2 and 3, or because everything here is a right angle. 5 and 6 are also right angles there. 5 and 6 together add to 90 degrees as well. So 90, oh, you can't see that. My head's in the way. So 90 plus 90 equals 180 degrees total. Those four angles together. 2 and 3 add to 90. 5 and 6 add to 90. Total they add to 180. And again, we don't know anymore that 2 is 30 and 3 is 60. You know, we're not basing that off, you know, this is a new problem. So kind of just keeping that in mind. But it still is consistent with the idea these are parallel. That these had to be right angles. Okay, got about 8 minutes left to kind of do things with my group that I have in here. So let's see if I can get the last 3 problems done. Use this diagram of trusses for a railroad bridge in exercise 14. Choo-choo. Come on, Mr. Robinson, you got 8 minutes left. Suppose BE is the perpendicular. Guys, this looks like one of those optical illusions to me. It looks like it gets fatter. It looks like the lines are kind of curved. Do you see what I'm saying? Suppose BE is the perpendicular bisector of DF. All right, perpendicular bisector. And by the theorem, guys, that also means that these two parts will be congruent. I'll draw them in green right now so you can see. By the theorem, it says that these points that are equidistant, or they are equidistant. This B is equidistant to the points D and F once we know this is a perpendicular bisector. Which of the following statements do you know are true? Select all that apply. Explain your reasoning. BD is equal to BF. I just stated that right here, and this is true. This is because of the perpendicular bisector theorem. Yes, that is very shorthand. Perpendicular bisector theorem states that BD is equal to BF. Measure of angle 1 plus measure of angle 2 equals 90 degrees. Well, I don't know, off the top of my head, guys, I don't know if I can guarantee this. You guys might say something like, well, I got, 2 lines cut by a transversal here, and I have alternate interior angles or same side that are supplementary congruent. Here's the thing. I don't think I yet know anything about AC. For all I know, because remember, guys, these drawings aren't drawn to scale. They just give you a drawing, they give you points, and they give you information. I know that these two parts are congruent based on perpendicular bisector. I don't know if AC doesn't maybe just look like this. For all I know, guys, AC could go from here to here. They didn't tell me these were right angles. They didn't tell me these were parallel. They didn't say anything about this being a perpendicular bisector of AC. I don't know what AC actually looks like in this regard. For all I know, it could look like this, which means I have no guarantee, even though I know this is a right angle, I have no guarantee this is a right angle. I don't know that for sure. I need more information, I think, to figure that out. Unless I can decide otherwise, I'm going to say I don't know that. E is the midpoint of DF. Yes, a bisector specifically goes through the midpoint of it. This isn't because of the theorem. This is because it's given. This is given information. I'll just write given. But guys, this is given information. Was the perpendicular bisector? It was given right there that they told you that it was specifically the midpoint, that it went through the midpoint. Measure of angle 3 plus measure of angle 4 equals 90 degrees. This one is true. If this one's 90, it doesn't matter which one I drew. If this one's 90, this one's 90 as well because it's perpendicular. Once again, excuse me, it's kind of given. It's given that it's 90 degrees, but this is because these are complementary angles based on the given. So these are complementary angles right here. And finally, DA is is perpendicular to AC. DA is perpendicular to AC. They're talking about this here. I don't have, once again, guys, there's no information that states that that's true. I don't see anything that tells us that. If it did tell us that, that actually would be conclusive that these would be as well because of perpendicular. There's just information that would make me say that. Well, actually, no, that wouldn't necessarily be true because I don't know if dA goes out like this or not either. Yeah, there's no information that tells us that, guys. I have no way of knowing for sure that would be the case. I only know stuff about this kind of upside down triangle, and that's about it. Anything else could be drawn any other way, and it doesn't upset the information that we're given. So these guys work out. The other ones don't work out. Okay, 15 and 16, last two. Number 15, two lines intersect to form a linear pair with equal measures. Okay, two lines intersect to form a linear pair with equal measures. So they're saying this is congruent to this right here. One angle has the measure 2x. The other has the angle measure 20y minus 10. Find the values of x and y. Explain your reasoning. Well, here's the thing. 2x equals 20y minus 10. Well, actually, I don't need to set them. I don't need to set these things equal. 2x and 20y minus 10 both equal 90 degrees. If these are both equal in measure for a linear pair, two angles that add, I shouldn't use x here, two angles, an unknown angle z plus the same unknown angle z, they're equal measures. If they add to 180, that means each measure is 90 degrees. So that means both of these are right angles. That's kind of what we talked about before. They're both congruent in a linear pair. They both add to 90. So 2x is 90, therefore x is 45. And 20y minus 10 equals 90. Let me use a different color. 20y minus 10 equals 90. Add 10 to both sides. I get 20y equals a hundo. And divide by 20, I get y equals 5. So it's based on that one theorem that we talked about. It's kind of more obvious than not that a linear pair with equal measures means they both have to be 90. To add to 180, they have to both be 90. So set them separately equal to 90 to solve them each. One more time, two lines intersect to form a linear pair of congruent angles. This is more or less the same kind of problem, so I can work kind of fast here. Congruent angles, once again, that makes them both 90, so I can draw little right angle symbols. Yee. The measure of one angle is 8x plus 10. And the other angle is 15y over 2. Find the values of x and y. So once again, it's very much the same. Set them equal to 90 and solve separately. So let's do that one more time, and then I will be all done. 8x plus 10 equals 90. Subtract 10 from both sides. 8x equals 80. Divide by 8 from both sides. X equals 10. The other one, 15y divided by 2 equals 90. I got to multiply both sides by 2. I'm dividing by 2 to get 90, so I got to multiply by 2 to figure out what it is. 90 times 2 is 180. And 180 divided by 15 is 12. So you get y equals 12. All right. Okay, so that'll be it for this video. That covers everything here. Anything that I cover here on out for this particular unit will be involving proofs. 2-column proofs at that, and I hope that I can get some videos that will cover that in a nutshell, for if not for all you guys out in Iowa and New Jersey, for my students themselves. So that'll do it from here, guys. This is Mr. Robinson. Thank you for watching.